Okay, I'm going to get rolling here on the second part of Remote Learning 7, and we're going to do a few more of the AP Calculus questions. These questions are from the non-calculator section, which generally means that they're a little more theoretical and I don't know if that's totally true, but yeah, they're theoretical and they expect you to do all the computations by hand. But then, of course, on this version, you'll be able to use the calculator. So I think they'll either ramp up the complexity of the functions or, I don't know, word it in such a way that you're supposed to show the process of differentiating or integrating. But I'll try to pursue these as if I'm not using a calculator and and then if that gets sort of ridiculous, then I'll switch to using a calculator. So as I mentioned in part one, it may be worth your while to pause and try these on your own before I pursue them, or at least read and wrap your mind around them so you're not trying to think through things while I'm talking. So do pause as you think you should. And here I go. So over here, there is a graph of the continuous function g, the derivative of f. So I might write that this is also f prime. And the function g, or the function f prime, is piecewise linear. So that means it's just a bunch of lines that are connected between -5 and 3. And then after that, it turns into this parabola with vertex at 4, 0, opening up twice as steep, as you can see from the function g at x. Okay, so part A is if we know the value of the function, now mind you, this is f prime over here, but if we know the value of f at 1 is 3, what is the value of f at -1? Okay, so what we need to find in order to do this is we need to know how much f changed as we went from -5 to 1. And the way that we write that in terms of calculus is that that would be the integral of the rate of change of f. Remember that the integral of rate of change gives total change. And so we want to know how much f changed from -5 to 1. And if we know what f is at 1, then we'd then be able to find what f was at -5. Okay, so then if we wrap our minds around this integral, it represents the total change on f at x over the interval -5 to 1. But in terms of the picture, the integral of f prime, the integral of this curve, is represented by the area trapped between the curve and the x-axis. So if we look at what's happening between -5 and +1, we can count all these areas. So I'm going to do it in 3 distinct pieces. Over here, the area is 9. Now keep in mind it's below, so I'm going to count that as a -9. This area is 3/2. That's 1/2 base times height of the triangle there. And then this area is equal to 1. Okay, so then that is a value of -9, -9.5. Considering these with their negative signs and this with its positive sign. Okay, so what we have is that the value of the function at -5, which is left of the value of f of 1, we would add to that the value that is the net change between -5 and 1, and then we would get the value of the function at 1. So the value of the function at -5 plus the amount that it's changed between -5 and 1 then gives the value at f at 1. And we don't know this one, but we do know this other one. Let's see. I'm going to sort of show this algebraically by adding the 9.5 over here and then turning f of 1 into its value of 3. Okay, so then that's my answer to part A. And now that it's up here, let's just sort of go through it one more time. If we know that the value of the function at 1 is 3, what is the value of the function at -5? I'm arguing that the value of the function at -5 is 12.5, because between -5 and 1, the function loses a value of -9.5, and if we subtract 9.5 from this, then we get the value of 3, like we're supposed to. Okay, so let's go on to part B. So let me scroll up and introduce part B. And part B is for us to evaluate the integral of gx dx from 1 to 6. Okay, now we have some of gx. We have like the parabolic function defined, and we can quite easily find all of these lines, but let's not get into all of those computations. Instead, let's think about what it means in terms of the picture. So we're looking for the amount of area trapped between the function and the x-axis between 1 and 6. So between 1 and 6. And I can see that the amount of area between 1 and 6 is, I've got this defined space in here, which is 4. Plus the area that we can find by using integral calculus, because we've been given this function, and it's also not something that you can eyeball. All right, now, clearly I could find this function and integrate it from 1 to 3 and also get 4, but since it's geometric, I can save some time doing that. So this is equal to 4 plus the integral of the parabolic part, which is 2x minus 4 squared dx, and we're going to run that from 3 all the way to 6. Okay, so we could easily do this on the calculator. Of course, this is in the no calculator section, so I'll see if I can do it by hand rather quickly. All right, so that constant 2 is out there, and I can integrate this. That is x minus 4 cubed, and then divided by 3 by the reverse power rule. And since the derivative of this is 1, I don't have to worry about any sort of like integral version of a chain rule. Again, only works when this is linear, but we've been through that a lot. Running from 3 to 6. Okay, yeah, and essentially this is 2/3. So, okay, so this is 4 plus, and then let's drop in some values. So when we drop in 6, we get 8/3 times 2, that's 16/3. And then we're going to subtract from that whatever happens when we drop in 3, which is -2/3. And so then that's 4 plus 18/3, that's 10. Okay, and then that's my answer to part B. Okay, so that is pretty easy, I think. And, maybe I've just sped things up a little bit by not turning this into two integrals. But you could have a bunch of pieces, and they're both positive, of course, because they're above the x-axis. All right, then let me bring up part C and see what we can do on this one. Okay, so here for -5 to 6, so we're looking at just this interval out here. On what open intervals, -5 to 6, we're going not 5 to 6, from -5 all the way out to 6. Let's get rid of this, so I'll have to be thinking about that. All right, so from -5 to 6, on what open intervals, if any, is the graph of f, remember this is f prime, is the graph of f both increasing and concave up? Give reasons for your answers. All right, so let's see. Let me first talk about increasing. So we want to find some places where f is increasing. So I'm just going to argue that f is increasing when f prime of x is greater than 0. Okay, so when the rate of change of f is positive, f is on its way up. Okay, so this happens on, okay, and then let's get these intervals where f prime is positive. Okay, so this is f prime. F prime is positive from 0. All of these are above the x-axis, so from 0 out to 6. Okay, so now we need to move on. That's that part. Now we need to move on to concave up. So f is concave up when f double prime is greater than 0. And maybe it's been a little while. Let's remember what's going on with that idea. Concave up. And then you can consider the slopes on each side, and they just went from negative to positive. Okay, so the rate at which the rate of change is happening is a positive thing. It's going from negative to positive. It's increasing. These tangent slopes are increasing. The tangent slopes are the first derivative. Their rate is the second derivative. So for concave up, f double prime is greater than 0. All right, so then this happens on, all right, and now we have to consider where f prime's derivatives are positive. So that's in all of these red zones. And over here. Okay, so those intervals are -2 to -1. And also from 0 to 1. And also from 4 to 6. Okay, so then our answer is when we consider both. So considering both, we conclude the intervals are 0 to 1 and 4 to 6. Okay, I've been putting boxes around things, so I'll again do that. All right, so recapping that one, we had to think about the relationship between f and f prime and f double prime. And it's really just really slowly thinking through what increasing means in terms of f primes, and that we have the f prime function, and what does concave up mean in terms of f double primes, and how do f double primes relate to graphs of f prime. Okay, and I laid that all out. And then it's taking these two subsets and finding where they intersect. All right. Okay, so next we're going to this last part, D. And let me read it and see what if I need to pull down the graph or anything. So find the x coordinate of each point of inflection of the graph of f. Give reasons. Okay, so what I remember about points of inflection happen when the function switches concavity. Okay, so then that happens when f double prime of x goes from positive to negative or negative to positive. Right? Points of inflection. That's where concavity switches. If f double prime is positive, it's concave up. If f double prime is negative, the reverse of this one, it's concave down. So where it switches concavity, the f double prime moves from positive to negative. So let's grab this picture. And think about f double primes and where, if anywhere, in fact, these f double primes switch. Well, f double primes are the slopes. So here, the slopes are 0, and they switch to being positive. Okay, well, that's neither of these. Here, they're positive, and they switch to being negative, to 0, so that's neither of those. Now they're switching from 0 to being positive again, back to 0, that's neither of those. From 0 to a negative, that's neither of those. And then here it switches from negative to positive. Okay, so that's the only place. So let's see, this happens at x equals 4. Okay, so there you go. That is one AP calculus problem in 4 parts. And I never did go to the calculator, but I kept reusing this picture. And it's a conversation about the relationships between f, f prime, f double prime, how they relate to the change in f, whether or not f is increasing or decreasing, how much it's increasing or decreasing. And then it's that classic scenario where we don't give you a picture of f, but we give you a picture of f prime, and then that makes you have to think about things more carefully. Okay, so then I have one for you to try, and it is over here. It's the second part of the assignment. Okay, I think you'll be in good shape with this one. Again, try not to use your calculator and think through the ideas carefully. When you get down to part D, things are going to get a little tougher. And in order to make this problem doable, in fact, I'm sure it's the way they want you to do it, you need to use something called L'Hopital's rule. And it's not something that we've gone over. The corner of the classroom at one point was talking about it months ago. But it's pretty easy to use L'Hopital's rule. And it's a way of changing this limit into a different limit, which turns out to be doable according to what this problem has given you. But you'll need to look up L'Hopital. So just do a quick search of L'Hopital, and they'll give you a formula, and I think you'll be able to tackle it from there. Okay, so thanks. Don't forget, you can create your own Google Meet and participate in a live board working together. I think that would be a great form. Okay, thanks everybody.